What's happening, folks? Geologist Philip Prince trying to answer a viewer question. Got a comment on another video asking about a very interesting feature along the Canadian coastline, the Laurentian Channel. Got to compliment whoever was looking at this. It's a subtle feature to see in Google Earth. I never really thought about it before, never looked at it before, but sure enough, it is there. You can see a little bit darker water there between those light blue lines, and that defines the outer parts of the Laurentian Channel, which sort of goes up to the edge of the shelf here. Viewer's question was, is this an ancient river valley? Did this form when sea level was lower and it's now flooded today? So we can answer that. The second part of the question was, why is there so much shallow water here off the coast of northeastern Canada? Got Newfoundland up here, Nova Scotia down into the northeastern U.S. Is that shallow water because this ancient river deposited a bunch of sediment here? So really good questions. Kind of in-depth stuff, more than just your usual Google Earth scouring. They have good answers, a lot of good stuff to think about: climate change, tectonics, what actually controls water depth on Earth, things like that. So the Laurentian Channel there is in an interesting part of the Western Atlantic Ocean. Of course, there is a lot of contrast in water depth. The Titanic wreck is actually in the view that we're looking at here. It's about 12,500 feet deep. Okay, so it's pretty deep, very close by, up on the Grand Banks. Water depth's only about 200 feet. So not a whole lot of difference in how far these two places are actually from land, from a shoreline, but a really big difference in water depth. Up there on the Flemish Cap, another kind of light blue area, about 600 feet deep. If you saw the movie Perfect Storm back in the day, they talk about the Grand Banks and Flemish Cap quite a bit. These are sort of shallow water areas that are right at the edge of the shallow water that you see kind of off the margin of the North American continent. So a couple other places for spatial reference here. Got Cape Cod down there, Nantucket Island. Both of those are sitting in what is, generally speaking, in the grand scheme of things, pretty shallow ocean water. Zooming out, northeastern North America, got the mid-Atlantic ridge here, really dark water out here in the abyss. Got Bermuda there, Florida, Gulf of Mexico. When you're looking at Google Earth, they color code water depth with color. The darker areas you're seeing here, out in kind of the deeper parts of the Western Atlantic, would be like 15 or 20,000 feet deep. Most of the light blue, particularly when you see it close to the continent, hundreds of feet deep. There's a little bit of deepening here. It'd be like a couple thousand feet deep here, east of Florida. So zooming in closer, might be able to see at Laurentian Channel a little bit better in this kind of tilted view. Again, Newfoundland up here for your reference. About 15,000 feet deep down in the really deep area there at the bottom of the screen. 250 feet or so kind of as an average on the northeast side of the Laurentian Channel. 500 feet deep right where 500 is there, but a lot of that area on the southwest side of the channel is just a few hundred feet deep as well. All right. In the channel itself, the water depth is about 1,400 feet. It shallows up a little bit right as you get to its edge here. Goes deep, goes shallow, goes deep. One way or the other, that's all you need to answer the "is this an ancient river valley" question. When Earth's sea level was at its lowest during the last ice ages, when a lot of water was tied up in glacial ice, the farthest sea level dropped below what it is today is about 400 feet. Right. So if the bottom of the Laurentian Channel was something like 300 feet below sea level and the surrounding areas were only about 100 feet deep, then yes, you would look at that and you say that might well be an ancient river channel. If it's 1,400 feet deep, that is far too deep to have been produced by river erosion when sea level was lower, right? So you can just look at that. You can look at that water depth and immediately answer that question. Now, that leads to another question. If it's not water, I mean, it looks like it's the continuation of the St. Lawrence River. What is it? It's big. It's about 65 miles wide. Sometimes you can kind of lose perspective when you're playing with Google Earth like this. It's a very large feature. Think about where you are. Go back to this previous slide. You're pretty far north here. We're up in Canada there. Of course, these big Great Lakes here that are very easy to see on Google Earth are glacial landforms. And sure enough, you can sort of apply that same logic here. So the Laurentian Channel is very much a carved feature. It is carved by frozen water in the form of glacial ice, sort of an ice cap kind of making its way off the continent and out towards the ocean basin. As I read, there's a lot of people that study this. It has a lot of very interesting biological aspects, just the depth contrast and the way water mixes. There's a lot of really interesting life and ecosystems here in the Laurentian Channel. There's quite a lot written about it, but the ice margin would have been somewhere off the coast here, maybe out towards the edge of the shelf or something like that. But one way or another, to produce something of that size and of that depth, you're going to have to get glacial ice involved in it. So even though it looks like a river channel, the depth test there is the real closing of the door on that one. And that's something that you can apply really around the world, right? If something that is under the ocean today is only a couple hundred feet deep, it would have been dry land probably more than once during the last ice ages. I don't know how much sea level rise and recovery there was in interglacial periods when a lot of the ice caps melted and the ice coverage reduced. But one way or another, that 400 feet below modern sea level as a maximum is a good reference point that you can use, right? So interesting example, the North Sea, say between Great Britain and the coast of Germany or the Netherlands or something like that, is only about 200 feet deep. Really horrifying body of water. I mean, like, look at a video of a North Sea storm, and I mean, it's quite intimidating to say the least. But it's in terms of oceans, it's really, really shallow, and that would have been dry land during the ice ages. Refer to it as Doggerland. People lived on it, animals lived on it. The people hunted the animals. A lot of artifacts get trawled up and dredged up out there. And there would be old river channels in a place like that because the water depth is still shallow enough today. Now, second question, why is there so much shallow water? Like, why do you have this really extensive 200-foot area coming off of Newfoundland here? And why is this part of the ocean that's 10,000, 15,000 feet deep or deeper so much different? And that's where you actually have to start thinking about plate tectonics, what makes a continent, what makes water depth, and things like that. So I am going to attempt to illustrate that with Microsoft Paint. You may wish to fast forward here, and you can probably like watch the progress. But I wanted to like draw out a diagram, kind of in the way a geologist would think about this, because it's a good question and it sort of shows a fundamental set of relationships. So wish me luck here. All right, so here we are on Microsoft Paint. Gonna see if I can draft out a block diagram here satisfactorily in enough time for people not to all bail on this video. You may wish to fast forward this. It might look kind of interesting, but what we're going to try to do is lay out sort of a block-shaped feature here that's going to give you a sense of what you might see if you cut open the edge of one of Earth's continents to expose the different types of rock down beneath it. Those different types of rock are ultimately what's going to be controlling things like where there's dry land, where water's deep, and so on and so forth. And if you've worked with geology and are watching this video, you may be able to get a sense of where this is going to go. But first big challenge here for the diagram is going to be to try to fill in some of these shapes with colors. And what we're showing with gray here, and we're going to have to get in there and like clean up the edges a little bit. What we're showing with gray is continental crust. Continental crust in Earth has a variety of compositions, but generally speaking, it's usually portrayed as being fairly similar to the rock type granite. which is often kind of a grayish material. And usually, if you're seeing continental crust portrayed in a diagram, some kind of a gray color is quite customary for that. Now, that's going to contrast with the oceanic crust that we're going to draw in a minute, which is going to be quite a bit easier than what we're doing here. So I'm going to kind of tidy up the edges here of our continental crust just a little bit. And if you use things like that polygon and solid fill tool there, sometimes paint will work out all right for you here. Okay, so we'll get the bottom of it cleaned up as well. Trying to stay in the lines. Say about 35 years ago, the life I was living at that time, coloring within the lines was a really big thing. So maybe we're doing all right here. Okay, so we got continental crust colored in there. This is going to be our oceanic crust. We're going to use black here because oceanic crust worldwide is sort of like basalt in its composition. In many cases, it straight up is basalt. You can get some variations there in the composition, probably along the edge of a continent here, because this is where continent split apart to actually form the new oceanic crust. There might be some variation in composition there right along the boundary, but generally speaking, basalt, like you'd see in Hawaii or something like that, although that is an ocean island related to a hot spot, that's the composition you're thinking of for oceanic crustal rocks, and it is a rock that is black in color. So that black there is going to be our oceanic crust. We're going to use some black lines here to represent some faults that have allowed the edge of the continent here to kind of break apart. And fundamentally, the reason that it has this funny shape is that it's been stretched, right? So say you had a section of Earth's crust like that, and you stretch, pull it apart. Because of the way rock behaves in the Earth system with the given mechanical properties of rock or its gravity, you're going to end up stretching the ends of it, and then in the middle there, it's going to end up being longer and thinner. And that lengthening, it doesn't all stretch like taffy or something might. The lower part of it can do that because that's where the rock is hot and ductile in the lower parts of the crust. The upper part where it's brittle is going to break apart, and kind of the signature you're going to see is something like that. You're going to see these kind of like stepped shapes. Those are normal faults that accommodate relative downward movement of the upper part of the fault system, and that's how this stretching gets accommodated in the earth, right? So we got normal faults, and they produce these little low areas, and we're going to fill those in with sediment layers. And we'll zoom in and add a little bit more detail in here momentarily, right? But those low areas provide little basins into which sediment can accumulate. Okay, so we got those set up here. We'll give it a little bit of variety. We'll get a couple of these green layers mixing in. Get a black shale or two in there as well. Okay, and then up on top of that, we're going to have even younger sediment layers kind of burying all that, and we'll just have those kind of draping down all the way there onto the oceanic crust. Okay, try to fill in a little more of the white there. And then on top of that, finally, we're going to have the ocean water. We'll do a darker color. Okay, so we'll fill in our little cross-section ocean water. You can see where I am right now above this broken crust with these accumulations of sediment. The water is pretty shallow. And then as I get out there towards that oceanic crust, the water is getting a whole lot deeper. And just get that all filled in. Dress this up with some indication of the layering there, like that. Okay, zoom back out here. Oops. Okay, so at this point, we got broken continental crust. Over on this side, got thick continental crust. So this will be something like, good writing. That'll be about 30 kilometers or more thick. By the time you get up here to where the oceanic crust, that's going to be like, oh, I don't know, less than 10, like 5 kilometers, 8 kilometers. We'll give it that range, something like that. Substantially thinner. Down underneath all of this, let's see if we can fire up another polygon here. Down here, you got rocks of the Earth's mantle. Mantle rocks, when you do see them at Earth's surface, which is rare, they are green. In most cases, the composition of them is dominated by green minerals. So we'll make that green there. Fill that in real nice. Get some labels going on here. So we got mantle, continental crust. Amidst all my diagrams, that didn't work well, did it? Oceanic crust there. And the takeaway here is the shallow water sits on top of the broken crust. The deep water sits on top of the oceanic crust. And then on that thicker continental crust, you got the dry land sitting up there, right? So if we'll try to fill in our ocean surface here as well. And ultimately, what you're seeing in this diagram is really, how you can look at shallow versus deep ocean water, certainly on the edge of continents around the world, and in many cases, even if it's not obviously, I guess you'd say, at the edge of a continent, the same doctrine holds true. So the thicker continental crust is what makes elevated land masses. Thinned continental crust tends to give you shallow water, and then oceanic crust is what has deep oceanic water sitting on top of it. Right now, an interesting detail of this, I'm not going to color my land in there. We'll put a river on it. We'll have the river. The river's bringing sediment out here into the ocean. Places like this get studied quite a bit because this is a really nice potential oil and gas province right here, right? So if you drill down into the sediment layers that are sitting in the basins on top of the broken crust, you might be rewarded with oil and gas. And places like this have been studied very extensively. Certainly in the 20th century when people have been able to do offshore exploration, and that's very much the case offshore of Canada. But before we hop out of here, the fundamental takeaway: thick continental crust gives you land, thin, broken continental crust with this sediment accumulated on it gives you shallow water, and then the oceanic crust is what gives you that really, really 10,000 plus feet deep offshore water depths. And the reason that maritime Canada has so much shallow water around it is it just has really extensive areas that have this broken continental crust underneath them. I Googled something like Newfoundland geologic cross section or something like that. Pretty basic search terms. Ended up with a scientific paper. You can see it there, get the authors off of it and everything. And sure enough, if you scroll down here and get to where they start showing representative cross sections, going to have to move the window here, flip it around, and you will see shapes that are going to be possibly familiar based on what I doodled in paint there, right? So what you got here is that same kind of broken continental crust with sediment accumulated on top of it, and that's cutting across the Grand Banks right there. So when you see this image, kind of think back to what you're looking at in paint here, where you have this pattern made by the stretched and broken continental crust. That broken crust isn't quite thick and strong enough to be buoyant enough to give you dry land. It also produces these little low areas that sediment can pile up in. That's what you're seeing in the scholarly article. And if you look at the journal that this article is in, is Marine and Petroleum Geology. So that's the real focal point of work like this. I mean, people are trying to understand the actual structures in that broken crust beneath the overlying sediment, because in the deeper basins there you can get the type of accumulation and the depth of accumulation that's going to generate oil and gas. So just about anywhere on Earth, if you're looking at a shallow shelf like this with dry land, big continental landmass on one side, this deep ocean water on the other side, and you don't see a really deep, dark trench there, like would be present on a convergent subducting margin, your mental picture should be that this shallow offshore water that's a couple hundred feet deep is underlain by this broken continental crust with a tantalizing accumulation of sediment on top of it, right? So that is the answer to that question in Canada in terms of why there's so much shallow water there. That zone of stretched and broken continental crust is just particularly wide there. That zone of stretched and broken crust extends all along eastern North America. If you were to zoom out and kind of project it down along the continental margin here, so we can get the annotator up here and zoom. If you were to draw this down along the continental margin, you would go from here, and it stretches further inland the further south you go. So I'm in South Carolina. We have that broken crust with basin filling sediments under our coastal plain, which is dry land. In fact, it goes up to a few hundred feet above sea level. That's the case all the way through North Carolina and Virginia. You can see the Chesapeake Bay there. And so Washington, D.C. would be something like where that big dot is there. Moving north of that, the basins are much closer to the coast. And then by the time you get up into maritime Canada, they're sort of in like these island land masses and offshore. But the same theme is there. And if there are drawings, if you were like a geologist thinking about places like this, trying to represent what's going on there, reading a paper about it, it's that pattern of stretched and broken crust like we drew out there that's going to be like first and foremost in your mind when you see a continental margin like that, right? So Laurentian Channel is an ice thing. You can tell that because of its depth. There is a big shallow area here, but that is not material that this potential ancient river has brought. It is covered in sediment, but fundamentally that shallow water is crustal architecture. That is not so much deposition in one spot as just the layout of the Earth's crust underneath it. So hopefully y'all enjoyed that paint drawing there. I hope somebody's like fast forwarding back and forth there. But just in terms of communicating geology, one of the things that you don't see much of in the world, you don't see much of it in school in most cases, is patterns like this. Like what shapes do you see in the Earth's crust where it gets stretched, for example? If you're around the discipline of geology, something like that is very familiar, and it allows you to sort of make these pattern-based relationships around the world to see how things work, and then get a sense of what might be under the ground, what you could expect from it, whatever else. All right. Hope you enjoyed it. See what else we can do with paint down the road.